Hey folks, in this video we're going to start with Newton's second law for circular motion, and in the video after that we're going to go through some problems. In this video, I'm going to focus on, once I introduce Newton's second law, just looking at a few situations and drawing free body diagrams for those. And basically, like, every situation I choose has some circular aspect to it. We start with Newton's second law. And what we have learned in previous videos is that the acceleration in this case is centripetal. So we talked about like the different types of acceleration. Because it's uniform circular motion, it's constant speed. And so there's no linear or tangential acceleration. There's only this centripetal acceleration. What that means is if this acceleration is centripetal, then the net force must also be in the centripetal direction. So net force C is centripetal net force, and that's equal to the mass times acceleration. Well, acceleration is v squared over r. So for centripetal acceleration, the net centripetal force is equal to the quantity mv squared over r. And let's look at that on a diagram. So if I have an object that is moving around a circular path, I can now draw three vectors to describe it. So I can draw the velocity vector. The object is always moving forward according to its frame of reference, but at the same time, it is also getting pulled toward the center of the circle. So we have centripetal acceleration is directed toward the center. And then the net force, because of how Newton's second law works, the net force has to also be directed toward the same point. And so the net force is going to be directed toward the center of the circle. So we have three vectors. Velocity points forward, centripetal acceleration, and the net centripetal force both point toward the center of the circle. And then as the object goes around the circle, all of these vectors rotate with the object's motion. So they're always pointed the same direction relative to the center of the circle. Okay, so a little bit about the name. So this net centripetal force. This is not the name of a new force, right? We know like the normal force, gravity, friction, tension. We aren't learning a new type of force. We are learning that there's another direction. We talked about the x-axis, the y-axis, parallel to an inclined plane, perpendicular to an inclined plane. The fifth direction that we're learning is the centripetal direction. So that just means the sum of the forces points toward the center of a circle. And it means nothing more or less than that. It does not tell you what type of force it is, because the truth of the matter is any force can cause the net centripetal force. So we have examples of every type of force that we've learned about and focused on being the cause of the centripetal force. A couple of things about using Newton's second law. First one is the positive direction is always toward the center. That's going to make things easier because this equation v squared over r does not have any vectors in it. It just has scalar quantities. So we need to make sure that we're choosing the right direction for that. It's not going to, we have to be like intentional about that. The other piece of advice is when you draw a free body diagram, so the free body diagram should be drawn as if you're next to the object. We're not going to take like a top-down look at things. We're going to look at things from the side. Sometimes in the case of like friction, we're going to look at the object as if we're like lurking behind it. But we were always going to be on the same level as the object. Okay, so something that can cause net centripetal force is if the road that you're driving on is bumpy, and not like a speed bump, like a big curve. So if you're driving through like the countryside and you go over a big hill, or you go down a hill and enter into a dip in the road, those sorts of things can cause a net centripetal acceleration. So let's start with the top of a hill. We only focus on the top of the hill because it provides us a simple view of the object. Now, the rule above, the center of the circle determines the positive direction, so down will be positive for this car. It's traveling at a constant speed over this hill, and we're going to draw the forces on that car. I'm going to just draw them right here. Now, the force of gravity is pointed down, so I'm going to put mg there, and then the normal force is pointed that way, and so down is the positive direction. So all we're doing is like analyzing the forces and writing things into Newton's second law. I'm not going to solve any problems today. So what this means, net centripetal force equals mv squared over r. The net centripetal force is due both to the force of gravity and the normal force. The force of gravity is in the positive direction, so I can write the expression mg minus Fn, and that is the expression for the net centripetal force. The force of gravity points into the circle, the normal force points out of the circle, and that's why gravity is positive and normal is negative. And that's equal to mv squared over r. So that's a good place to stop for this one, but I want to go one step further. I can solve this for normal force. And one thing we've learned about in this unit already is that normal force is a way to represent the apparent weight of something. If I solve this for normal force, I get mg minus mv squared over r. And what that means is the normal force is equal to the actual weight of the object minus the net force. This means that you have a lower apparent weight than actual weight in this situation. So when you go over the top of a hill, you can feel lighter, especially if you're going really fast, and the physics shows us why. This is the same thing as like the elevator problems, except now you're traveling in a circle. All right, next one is at the bottom of a dip. This is really like a roller coaster moment, right? You go down the first hill of a roller coaster, and then the first thing you usually do is you come right back up really quickly, and you feel like you're getting squished into the seat of the roller coaster. So the diagram for this one is going to be the same, mg down, Fn up, but because the center of the circle is now above, up is now the positive direction. So we write the same forces, we just write them in a different order. So the net centripetal force is mv squared over r. And then our expression for net force is going to be Fn minus mg equals mv squared over r. So again, like whatever the problem is that you're solving, this is the general way that the forces set themselves up. If you happen to solve this for Fn, you get mg plus mv squared over r. So these two expressions have the same format, except one is subtraction, one is addition. When you get to the bottom of a dip, you have a higher apparent weight. Okay, so that takes care of like probably the most common setups for AP Physics 1. I have two more, however, that are going to be important to us. Taking a turn in a car is a critical one, and I drew a really fancy drawing for my art skills on this one, where the car is going to be taking a right turn, setting up the positive direction as to the right. So this is not how the rotaries are set up in the United States. We go, if you're looking top down, we go counterclockwise around the rotaries. This would be a clockwise rotary, so imagine a turnabout in England. And we're going to draw the forces for this car. Now, I'm going to draw this diagram as if I am sitting behind the car. I'm in a car that's like tailgating this car, and both of us are about to take this right-hand turn. So the normal and gravity forces are kind of obvious if I look at where the ground is. And then the important thing here is like the static friction force is necessary to keep me turning. The static friction force is what grips the road and pulls me, or pushes me rather, toward the center of the circle. So I keep going around in a circle because friction is doing that pulling. So that is going to make my net force expression fairly simple. I'm going to go through a few things pretty quickly right now, and you can stop and ask me questions if you're watching in the room, or you can save questions for me for tomorrow if you have them. According to this, the positive direction is in the same direction as the static friction force, and there's no other horizontal forces. So the static friction force is the net centripetal force in this situation. Now, the problems involving static friction and driving are going to be ones where it's thinking about, like, what is the fastest speed you can have so that your tires don't lose grip with the road. So we're going to use the expression for maximum static friction force, mu times the normal force. And when I solve this equation for something, it is going to represent a situation where the tires are at their limit. They are producing the maximum amount of friction because I'm going as fast as I can without losing traction on the road. If I look at my free body diagram, cars are going to be driving on flat ground in this situation, and so the normal force and the force of gravity are equal, and so I can write the following expression. When we get into the next unit, this mu mg is going to come back, so we'll be seeing that a lot in physics. If I look at this expression now, I have a mass in both terms, and so if I divide by m on both sides, I can cancel that. I have mu s times g equals v squared over r. And whatever the problem is, you can now solve that little equation. But the point is, there's no mass. So what that communicates is mass cannot affect the outcome. Now, this is according to our simple model of friction. In practice, the mass of a car is going to make a difference, and also how that mass is distributed inside the car. But for our simple model of friction, the mass cancels, and so that tells us the mass does not affect the turning of a car utilizing static friction. I know the video is running long, and I'm going to do one last example, and that's the loop-the-loop. So we have a car that's like driving around a circle, like a stunt car doing a loop, and we're going to draw some forces for that. Down is positive, and so when I draw my diagram, I have to think about, okay, I have gravity pointed down, because it's always down. And in this case, the surface is above the car, and so the normal force is also pushing down. And so let's look at Newton's second law and maybe what that says for our car. So the normal force plus the force of gravity is equal to mv squared over r. So there's a couple things I can do with this. The net force is equal to the sum of these two forces. Now keep in mind that mv squared over r is equal to m times a. The acceleration of this car is therefore due to the weight of the object plus that force. That's like an extra downward force on this object. So under these circumstances, the acceleration of that car is greater than g. The downward acceleration of this car is greater than the acceleration due to gravity, because not only is gravity pulling down on it, but the car is being pushed down by the loop itself. The last thing about this is sometimes what I'm going to ask you about on this is if the car loses contact with the loop, what happens then, or what does the expression look like then? So we had Fn plus mg equals mv squared over r. If the car is going to lose contact with the loop, then the normal force is going to become 0. The normal force is only the force due to the surfaces pressing against one another, and so if the car loses contact, then that's it. What we're left with is mg equals mv squared over r, and the mass cancels again. We get g equals v squared over r. Now, this v squared over r, I probably shouldn't have plugged it in, because what I want to show you is that in the first video, we learned that v squared over r is the centripetal acceleration. And so this expression tells us that the centripetal acceleration is equal to g. So if the car loses contact with the loop, it becomes a projectile. And projectiles have accelerations that are equal to little g. And so this expression proves that that is going to happen. All right, I know that was a long video, but that takes care of the majority of the situations you will see involving a net centripetal force. Thank you.